All right, today we'll be working on graphing function using derivatives and other known facts about the function. We are not going to use calculator or any other graphing tool, but we are purely using the concept of calculus that we have explored so far to sketch the graph of the function. In order to sketch the graph of the function, there are few steps or there are few facts that you need to find about the function. So we can graph the function or graph a function y equal to f of x by finding some or all of the following facts about it. So these are the things we are going to find before we start sketching the graph of the function. First, we need to identify the domain or the interval of interest. So by looking at the function or by analyzing the function, we must find the domain of the function. Second thing, we have to find the first derivative, and using that first derivative, we have to find the critical points, which will help you find where the function is increasing, where it is decreasing, or where it will remain constant. Third step, you have to find the second derivative, and using that second derivative, you have to find the inflection points, and using that, you must be able to determine where the function is concave up or concave down. That's step 3. In step 4, we have to find the asymptotes and intercepts. If there are any asymptotes or if there are any intercepts, we are going to find those in 4th step. And the 5th and the final step is you have to find some additional point, find some points on the graph of the function, including the critical point, inflection point, and some other points that will help you to sketch the graph of the function. So these are the 5 main steps that you have to follow while graphing or while sketching the graph of a function. One more time. First, you have to find the domain. Second, you have to find the first derivative and the information that you'll get from there. Third, you have to find the second derivative and the information that you'll get from there. Fourth step, you have to find the asymptotes and intercepts. And fifth step, you have to find some points, additional points that might be helpful in sketching the graph. And hence, we have to sketch the graph of the function. Example, sketch the graph of the function f of x equal to e raised to x over x without using technology. That's without using the graphing calculator or any other graphing software. We have to sketch the graph of this function. So first step is to find the domain of the function. So step 1, let me write step by step. Step 1, we have to find the domain of f of x equal to e to the x over x is, you know that this function e to the x over x is well defined for all values of x except x equal to 0. If you plug in 0, denominator will be 0, and you cannot define that. So the domain of the function is all x except x equal to 0. X equal to 0 is not the domain. That means when you sketch the graph of the function, if you think of the number line or x-axis goes from negative infinity up to infinity, you'll have graph all the way from negative infinity up to positive infinity except at x equal to 0. At x equal to 0, there is no graph. There is something there. So except at x equal to 0, your function is well defined. So that is the domain of the function. Okay, step 2, we are going to find the first derivative of the function. Our function is e to the x over x. So in order to find the derivative of this function, we have to use the quotient rule. So the first derivative is equal to, if you use the quotient rule says denominator, which is x, times the derivative of numerator, derivative of e to the x is e to the x, minus, we did denominator times the derivative of numerator, minus the numerator. Numerator is e to the x, multiplied with the derivative of denominator. Derivative of x is 1, divided by the square of the denominator. The square of the denominator is x squared. So if you try to simplify this, you can factor out e to the x. So it will be e to the x, then you get x minus 1 over x squared. So this is my first derivative. First derivative will help us to find the critical numbers. And the critical numbers are the numbers where the first derivative is 0 or undefined. So let's see, if the first derivative is equal to 0, then what I'm saying is, when I say first derivative is equal to 0, I'm saying that this fraction is 0. The fraction will be 0 only when the numerator is 0. That is when e to the x multiplied to x minus 1 equal to 0. E to the x is never 0 because it's always a positive quantity. Whatever the value of x may be, e to the x is always a positive quantity. So positive quantity multiplied to the quantity inside the parenthesis must be 0. And we know that x minus 1 will be 0 when x is equal to 1. So that is x equal to 1. So x equal to 1 is a critical number. And if you want to show it here in our domain, x equal to 1 will be somewhere there. So that is x equal to 1. This is the place where the first derivative is 0. So there is first derivative 0. And also, the first derivative will be undefined. Let's write it down. If the first derivative is undefined, then what I'm saying is this fraction is undefined. The fraction will be undefined when the denominator is 0. That is when x squared equal to 0. That is when x squared equal to 0 or x equal to 0. But x equal to 0 is not there in the domain. That is not the point in the domain. So this is not in domain. This is not in domain. So what we got is, by using the first derivative or by calculating the first derivative, we are able to get a critical number that is x equal to 1. Now, using that critical number, we have seen that our domain is divided into a couple of intervals. The first one is from negative infinity up to 0. We don't know what is going on at 0. And then from 0 up to 1. And then from 1 up to infinity. Now, because we have the first derivative, we'll be able to find where the function is increasing and where it is decreasing. So the function will be increasing if the first derivative is positive. It is decreasing when the first derivative is negative. And it is constant when the first derivative is 0. So we are going to check each of these. So let's see, when the value of x is equal to -1. -1 means I'm plugging in value from here. When x equal to -1, the first derivative will be f prime 1 will be, if you plug in 1 here, this will be e to the, I'm plugging in -1. So e to the -1, e to the -1, and it will be -1 minus 1, -1 minus 1, divided by -1 squared, because we are plugging in here. So over here, -1 minus -1, that is -2. -2 divided by -1 squared, that is -2. -2 multiplied to e to the -1 is -2 over e, because e to the -1 is same as 1 over e. So we get the first derivative negative. Over here, the first derivative is negative. So we can mark that over there. First derivative is negative. Meaning of that is the function is decreasing. So the graph is decreasing over there. You want to sketch the graph of the function. It is decreasing there. Now let's check here from 0 up to 1. What is going on in this interval? From 0 up to 1, you can plug in any number from here. I'm going to take half. So if I plug in half, when x is equal to half, the derivative at half is equal to, the first derivative at half is equal to, if I plug in half here, e to the half, that is square root of e, multiplied to, we have x minus 1, so half minus 1, divided by x squared, half squared is 1/4, which is equal to, now over here, half minus 1 is -half. -half divided by 1/4 is -2. -2, and there is a square root of e. So -2 is square root of e. That means in this interval here, the first derivative is negative. Here the first derivative is negative. Meaning of that is the graph is decreasing, or the function is decreasing. When you go from left to right, from 0 up to 1, the graph is going down. It is decreasing. That is the meaning of that. Now let's try one more. Over here in this interval, let's see what is going on. So when x equal to, let's take some value from here, maybe x equal to 2. When x equal to 2, the first derivative at 2 is equal to, if you plug in 2 here, it will be e squared, and then 2 minus 1 is 1. 1 times e squared, that's e squared, divided by 2 squared is 4. So we get e squared over 4. E squared is a positive quantity divided by positive, so the value is positive. So here in that interval, the second derivative is positive. Meaning of that is the graph is, or the value of the function is increasing, or the graph is going up when you go from left to right. So these are the information that we get from the first derivative of the function. So this is the second step in the preparation of graphing or sketching the graph of this function. So far, we got the first derivative, which is equal to e to the x times x minus 1 over x squared. We know that the domain is from negative infinity to infinity. We don't know what is going on at x equal to 0. Now we are going to get more information about the function using the second derivative. So let's find the second derivative. Now the second derivative of the function is equal to, we have to be very careful when we calculate the second derivative here, because there are a lot of functions involving there. What I'm going to do is, when you look at it, this is the quotient, so I'm going to use the quotient rule. Quotient rule says denominator, which is x squared multiplied to the derivative of numerator. Let me write the derivative of numerator in a bracket. In order to find the derivative of numerator, you can see numerator is already in the form of a product, so we have to use the product rule there. Product rule says first function e to the x multiplied to the derivative of second, derivative of x minus 1 is 1, minus, I'm using the product rule, so plus first function times the derivative of second, plus second function x minus 1. So we'll write the second function there, which is x minus 1, and multiply by the derivative of first e to the x. So what we have done so far is we did denominator times the derivative of numerator. This is the derivative of numerator. Then minus, we'll write the numerator, which is e to the x, x minus 1, that is numerator, multiplied with the derivative of denominator. Derivative of x squared is 2x. And we divide all this by the square of the denominator. The square of x squared is x to the 4. X to the 4. Now we have to simplify this very, very carefully. So this implies the second derivative of the function is equal to, now when we simplify here we have e to the x, and here also we have e to the x. So we can factor that e to the x out. So it becomes e to the x, there is already x squared outside. And when you factor e to the x out from here, we have 1. And then when you factor e to the x out, you have x plus 1 remaining. I mean x minus 1 remaining. Then minus, over here we have e to the x, and then you can multiply this. 2x multiplied to x, that is 2x squared. Then minus 2x multiplied to 1 is 2x. All divided by x to the 4. Next step. Now inside the parenthesis, you can see here, there's a negative 1 and positive 1. It will get cancelled. So you have x multiplied with that. So it becomes e to the x multiplied to x cubed. E to the x multiplied to x cubed. And then you have a minus, you have e to the x multiplied to 2x squared minus 2x. And in the denominator, we have x to the 4. Let's go further. Now you can clearly see here we have a x, here is x squared, And here we have x cubed, so you can factor out x, and also you can factor out e to the x. So if you factor out x times e to the x out, you are left with x squared minus, now negative, when you distribute, that will be negative 2x minus 2, all divided by x to the 4. Now we go further and simplify that. You can see here is x and here is x to the 4, so it will divide. So in the denominator, you will have x cubed in the denominator, e to the x in the numerator, and also you have x squared minus 2x plus 2 in the numerator. So that is our second derivative. Once we get the second derivative, we can find the inflection numbers, and we can find where the function is increasing, where the function is concave up and where it is concave down. So let's work on that part now. If the first derivative is equal to 0, then what we are saying is, we are saying that the numerator is 0. And numerator will be 0 only when the quantity inside the parenthesis is 0. That is when x squared minus 2x plus 2 equal to 0. This equation has no real solution. This equation has no real solution. So we don't get any number which are the inflection number, and that goes into the domain from negative infinity to infinity when we take the first case. That is, when the second derivative is 0. Now let's take the second case, when the second derivative is undefined. If second derivative is undefined, then what I'm saying is this fraction is undefined, and this fraction will be undefined when the denominator is 0. So then x cubed equal to 0. X cubed will be 0 when x equal to 0. So we again get x equal to 0. So this implies x is equal to 0, and this is also not there in the domain, not in domain. So the only possibility that we have, we didn't get any number to put here on this domain from negative infinity to infinity. Just because of that 0, we have two intervals. We have an interval here from negative infinity to 0, and there is another interval from 0 up to infinity. So we are going to check in these two intervals whether the function is concave up or concave down. So now let's try to do that. If you plug in, or let's say when x equal to, let's try to plug in any number from here. So when x equal to -1, what will be the second derivative? Second derivative at -1 is equal to, if we plug in -1, this will be 1 over e to the -1 is 1 over e, and then 1 squared, -1 squared is 1. 2 times -1, that's plus 2. And also there is a plus 2. And we are dividing all that by -1 cubed, which is -1. Now you can clearly see what we are getting here is negative, because we are dividing by -1. So negative 2 plus 2, 4 plus 1, 5 over e. -5 over e. We get negative value over here. Our second derivative is negative in this interval from negative infinity up to 0. It is negative. Meaning of that is your graph is concave down here. So your graph is concave down. Now we are going to check here by plugging in +1. Let's try to plug in +1. So when x equal to +1, when x equal to +1, so I'm selecting a value from here, a +1, and then I'm plugging into the second derivative.
If I plug in 1, it will be e to the 1, which is e. And then here we have 1 squared, which is 1. Minus 2 times 1 is 2, minus 2. Then we have a plus 2 divided by 1 cubed, that is 1, which is equal to, you can see here, 2 and 2 cancel. We have 1 times e. E divided by 1, that is e. E is approximately 2.7. So we got a positive number. So second derivative is positive in this interval. From 0 up to infinity, the second derivative is positive. Meaning of that is your function is concave up here. So concave up. So when we draw the graph, we have to draw it concave up. So in step 4, we'll be finding the asymptotes and intercepts. We know that the domain is from negative infinity to infinity, except x equal to 0. First, let's try to find the asymptotes. We have our function. The function is f of x equal to e to the x over x. And we already know how to find the limit, so I'm directly going to write the limit. If you try to find the limit as x approaches to 0, when x goes to 0 from the left and from the right of this function, e to the x over x, you can find this limit by any method you want. You'll see that the limit is infinity. The reason is when you plug in 0, it will be e to the 0, which is 1, and you are dividing by a number which is close to 0. When you divide 1 by a number which is close to 0, it's a big number, it's an infinity. So when x approaches to a finite value, the value of the limit is infinity. Meaning of that is x equal to 0 is vertical asymptote. That is the vertical asymptote. So we were looking for something here at x equal to 0 because x equal to 0 was not in the domain of the function. Now we know that x equal to 0, at x equal to 0, you have a vertical asymptote. So this is how we find the vertical asymptote. Now let's try to find the horizontal asymptote. To find the horizontal asymptote, we have to find the limit when x approaches negative infinity and x approaches positive infinity. So limit as x approaches to positive infinity of e to the x over x. You can find this limit by any method you want. This should be equal to, what I'm going to do is, in order to find this limit, I'm going to use a special rule called L'Hopital's rule. And in L'Hopital's rule, because if you try to plug in infinity, it will be e to the infinity, which is infinity. And also in the denominator, it will be infinity. It will be infinity over infinity or indeterminate form. And if you are calculating the limit of the indeterminate form, we can use a L'Hopital rule. And this is how we find that. Limit as x approaches to infinity, we find the derivative of numerator and denominator. Derivative of numerator, derivative of e to the x is e to the x. And derivative of denominator, derivative of x is 1. So we are calculating the limit as x approaches to infinity of e to the x over 1. If you try to plug in infinity, now e to the infinity is equal to infinity. So here, when you try to find the limit as x goes to infinity, that is towards this side, towards the right end, when x goes to infinity, the function is also going to infinity. So there is no horizontal asymptote. So meaning of that is there is no horizontal asymptote. There is no horizontal asymptote when you go to the extreme right. Now let's check what is there on the extreme left. If we come to left, let's find out what is there. Limit as x approaches to negative infinity of e to the x over x. So in this case, if you try to compute the limit, same thing, it will be infinity over infinity. So you can use that L'Hopital's rule, that is finding the derivative in the numerator and denominator when x approaches to negative infinity. So your numerator, derivative of e to the x is e to the x, and denominator will be 1. That is equal to, now if you try to plug in infinity, e to the negative infinity is 0. So 0 over 1 is 0. So when you find that limit, this is equal to 0. So meaning of that is as x approaches to negative infinity, when you go to infinity on this side, the graph of the function gets closer and closer to 0. That means y equal to 0, y equal to 0 is horizontal asymptote. We get x equal to 0 as the vertical asymptote and y equal to 0 as the horizontal asymptote. Now, in order to get these intercepts, let's try to plug in x equal to 0. When you plug in x equal to 0, you'll get the y-intercept. So if you plug in x equal to 0 to the function, when x equal to 0, the value of the function, that's also the y value, you can write y equal to, if you want, is equal to e to the 0 over 0. That will be equal to e to the 0 over 0. E to the 0 is 1. 1 over 0 is undefined. Undefined. Meaning of that is, when x equal to 0, we are not getting any y value. If you get the y value, that will be the y-intercept. But we are not getting anything. Meaning of that is, there is no y-intercept. So meaning of that is, there is no y-intercept. There is no y-intercept. Similarly, when you plug in y equal to 0, when y equal to 0, when I say y equal to 0, that is, I'm saying that this value is 0. 0 is equal to e to the x over x. So here we have a fraction equal to 0. Fraction will be 0 when the numerator is 0. So meaning of that is e to the x equal to 0. And e to the x cannot be 0. E to the x equal to 0, this is impossible. E to the x is never 0. That's not possible. So meaning of that is, see, when y equal to 0, I'm not getting any x value. So meaning of that is, there is no x-intercept. So let's write that. There is no x-intercept. So x-intercept is not there. Y-intercept is not there. Step 5, additional points and sketching the graph. So in order to find the points, we make the table of values, and we are going to take few points. Say for example 0, and then 1, maybe a 2, 0, 1, 2. Also take one negative value, maybe negative 1. So let's find some points on the graph of that function. Our function was f of x equal to e to the x divided by x. We have already seen when you plug in x equal to 0, it will be undefined. So 0, at 0, it is undefined. Undefined, that's how I'm writing it. If you plug in 1, it will be e to the 1 divided by 1. That is equal to e. The value of e is approximately 2.7. So I can write 2.7. And then if I plug in 2, it will be e squared divided by 2. So if you simplify that using calculator, e squared divided by 2, that is approximately 3.7. And then if you plug in negative 1, it will be negative 1 over e, which is negative approximately 0.4. So these are the points that we need while sketching the graph. Now let's draw the grid for the graph. That is, let's draw the x and y axis for the graph. Suppose that is my x-axis going from negative infinity up to infinity. And also let's draw the y-axis. Suppose that is my y-axis. I'll write y there and y prime for the negative part. We saw that at x equal to 0 and x equal to y equal to 0, we have the asymptote. So what we know is x equal to 0 is this vertical line. This is x equal to 0. X equal to 0 is vertical asymptote. So we can say that this one is x equal to 0, which is the vertical asymptote. And also we have the horizontal asymptote y equal to 0. So this, all values on the x-axis is y equal to 0. So this is y equal to 0, or that is your horizontal asymptote. We have those two pieces of information. Now let's plot some points. If I go here, -1, and we have -0.4, it should be somewhere there. Let's label this x and y axis a little bit so that it's easy for us to sketch the graph. So like -1, -2, -3, -4, -5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. We can do the same thing below the x-axis. So -1, -2, -3, -4, -5, and -6. Okay. So let me take the first point. I'm going to graph in the negative side first. So when we have -1, it is -0.4. -1 and -0.4 is somewhere there. So you can plot that point. -1 and -0.4 is there. So what this indicates is that the value of the function when x is less than 0 is negative. That's why the value is negative here. Also, we know that this line, this is the horizontal asymptote. This is the horizontal asymptote and this is the vertical asymptote. That means the graph will not touch the x-axis. It will go closer to the x-axis, but it will not touch. And also, this side, the graph will go closer to the y-axis, but it will not touch. Now, let's analyze something. This is -1. For all values less than -1, if you go here, for all values less than 0, actually, for all values less than 0, the graph is decreasing. For all values less than 0, the graph is decreasing. That means when you go from left to right, the graph is going down, it is decreasing. And also, in the same interval, from -infinity up to 0, the graph is concave down. It is facing down and decreasing. That means your graph will be something like this. You can see when you go from left to right, it's going down and is also concave down. So it's facing downward and it's decreasing and it's facing down. That is the meaning of that. So we have the graph for the values less than 0. At 0, we have the vertical asymptote, we know that. Now let's take few values here. Suppose when x equal to 1, we have 2.7. So when we have 1, the value is 2.7, somewhere there, 2.7, 2.7. 1 and 2.7 is that dot. And then after that, when it is 2, it is 3.7. When it is 2, it is 3.7. If you are at 2, it is 3.7. It's going up now. 3.7. So that is a 3 and 0.7. So it is there. Now what we know is this is the vertical asymptote. Meaning of that is the graph over here must be getting closer and closer to y-axis. So if you go and check there, you can see that after 1, you can see up to 1, the graph is decreasing. See, up to 1, the graph is decreasing. But up to 1 here, it's concave up. So concave up and decreasing. So the graph is like this. Concave up, you can see it is concave up and is decreasing. But after 1, check there. After 1, the graph is increasing. And also after 1, or for everything from 0 up to infinity, it is concave up and increasing. So from here, it is concave up and then increasing. So that is the graph of the function f of x equal to e to the x over x. So this is how we can sketch the graph of the function using calculus.